Hello, everybody. Okay, so this presentation is going to be about finding the volume of a three-dimensional solid object. And the objects that we are going to be finding the volume of, the way we are going to think about them is that there's going to be a certain region on the plane that's going to be the base of the object. And then on that base area, we're going to make this 3D object by putting on cross sections that all have the same shape. And then whatever the width of the base area is at a certain place, that's how large the cross section is going to be. So I know that sounds like kind of wackadoodle, so there are some pictures in here to try to help us envision what this is going to look like. So in this first example over here on the left, our base area is a circle. And so when we start over here on the very left, the width of this, and the cross sections are squares. So our base area is a circle and we're using square cross sections. So when we start over here on the far left, the base of the square is not very large, so we're going to have very teeny squares. And then as we move to the left, the squares are going to get larger and larger, and then our largest square is going to be right here in the middle, and then the squares are going to start to get smaller again to over here. So that generates this solid. So over here, you can see this is where the tiniest square cross section was. So this point might have been over at the far left, and then we just kept stacking square cross sections that were getting taller and taller, and then you can see this is where like the tallest square cross section was. This is right on top of the y-axis, and then we kept adding, and they get smaller and go down on the other side. Same deal here. Here we're using a base area that's a semicircle, and then the cross sections are equilateral triangles. So the first triangle is going to be really tiny, right here. And then the equilateral triangles are going to get larger and larger. This green bar is one of the bases of the triangles. And over here you see the solid that's generated. Here's a small triangle. And then they get larger and larger. And so on and so forth. And then they get smaller on the other side. Here are a couple more examples. Here, the base area is a circle, but we are, the base area is a circle, so we've got a circle in the plane, and then we're using equilateral triangles as a cross section. So there's one at the widest point right here. That's when you're going to get the largest triangular cross section. And it makes a shape. I can actually bring one of these into class, but it has a round base and then kind of like a pointy edge on the top where the triangles are. And then over in this last picture, we are using the area underneath y equals x squared as the base area. So right in here. And we have 4 different types of cross sections that were built onto this area. The first one is squares, so that's squares. I believe these are 30, 60, 90 triangles. Here the cross sections are semicircles, and then I think in this one they're using rectangles that fit a certain ratio, like they're half as tall as they are wide or something like that. Okay, so why do we do this? Well, so we can use calculus and specifically integration to find the volume of any of these shapes. The way we're going to think about it is, if we're thinking about, if we know a base area and we can figure out the length of one side, and that's going to be one side of a cross section. As long as we know the shape of the cross section, we actually are pretty good at being able to figure out the area of a two-dimensional cross section. So we're going to use this length to figure out the area of a cross section, and then we're going to imagine adding up, we're going to integrate all of those areas, add up all those areas, imagine that we're adding up the area of a bunch of super thin slices of a shape, and when you add up all those areas, you get the volume. So let's take a look. So we're going to start off with an example where we are using a base area that is a circle with a radius of 5, and we're going to use circular cross sections. So this should end up producing a sphere, right? If we use a so there's our base area. If we use circular cross sections and we build them across like this, we're going to end up getting a sphere. So this is a sphere with radius of 5. The volume should be 4 times 125 pi over 3. So we know what the answer should be in the end, so we'll be able to check ourselves. Okay, so the way I'm going to think about this, the equation for a circle, or at least the top half of a circle, is y equals 25 minus x squared. So that is the equation for this top portion of the circle. So we're going to imagine we're starting over here, and we're going to start building these cross sections. The length from the function, the top of the circle, down to the x-axis, that is going to be the radius of the cross section that we're looking at. So if you imagine, the circular cross section that would be right here. You can't see it in 2D, but it would be something like this. Okay. The radius of that cross section is the distance from the axis up to the circle. So when we think about the area of these circular cross sections, their area is going to follow the formula for the area of a circle, which is pi r squared. But this r, as we move from left to right, this r is just going to be square root of 25 minus x squared, because that is the distance from the x-axis to the circle that we are integrating across, and that's going to be the radius that we want to use to find the area of the cross section. So we want to integrate from -5 to +5. We want to start over here and work our way all the way across the circular base area, and as we integrate across, we want to be adding up the area of each circular cross section. So that's going to be pi times root 25 minus x squared dx. So this piece is the area of a circular cross section, of each circular cross section. And we want to add all those up of all cross sections from x equals -5 to +5. Okay, so go ahead and put that in your calculator, and let's check and see if we get the same thing, 4 times 125 pi over 3. Okay, before you put it in the calculator, we've left off something important. So the area for the formula for the area of a circle is pi r squared. So we've got the pi, we've got the r, but I forgot the squared. This whole thing needs to be squared. Okay, so now go ahead and put it in your calculator. And from the calculator we get that this is 500 pi over 3, which in decimals is 523.56. And that is exactly what we get when we used the 523.6. That is exactly what we get when we use the geometry formula to find the volume of the sphere. So the volume of the sphere is 500 pi over 3. Okay. So this time we're going to use the same base area, but the cross sections that we are going to use are going to be equilateral triangles instead of circles. So again, this distance in between the top of the circle and the bottom of the circle, that's going to be the side length S of these equilateral triangles that we are building up here on top of the circle. So this might be a cross section. It's hard to draw it so it looks equilateral, but it needs to be an equilateral triangle. So like, my artistic skills are not great, but anyway, okay, so for each, so we want to go, we still want to integrate from -5 to 5. So that's the left and right bound of our base area. We need to figure out an expression for this side length, right? So the top half of the circle is still y equals square root of 25 minus x squared. So if the distance from the x-axis up to the top of the circle is 25 minus x, square root of 25 minus x squared, then this whole distance from top to bottom is just going to be twice that length. So the base of this equilateral triangle, as we go across, is going to be 2 times the square root of 25 minus x squared. So if that's the base, what is the area of the triangle on that base? So the area in an equilateral triangle, some of you may know this formula, some of you may not, is just the side length squared times the square root of 3 over 4. So this is going to be a pretty handy area formula in this unit. Okay, so if the base of our triangles is 2 times square root of 25 minus x squared, then the area that we want to integrate is going to be 2 times root 25 minus x squared squared root 3 all over 4. So this is what we need to integrate. So again, this piece just gives us the area of each cross section, and then we are adding up those areas from -5 to +5. So you can go ahead and punch this in your calculator and see what you get. Okay, so when we put that in the calculator, we get that the volume of this solid is going to be 500 root 3 over 3 cubic units. Okay. So we can use any region in the plane that's bounded to serve as the base area. So here, this should look familiar. It's one of the graphs from the previous area between two curves presentation. Okay, so we're going to use this base area to form a solid that has square cross sections. Okay, so what I want you to do is first to figure out the bounds of integration. Okay, this part should be familiar. We set the f of x equal to g of x and solve. You can either solve by hand or use the solver in your calculator. You're going to get that this region is bounded from x equals 3, and then they are equal again at x equals 5. So our bounds of integration are going to be from 3 to 5. Okay, so next what you want to do is write an expression for the distance from the top curve to the bottom curve, because that's going to be the base of each square. So go ahead and write an expression for that. Okay, so the side length of each square is just going to be the red function minus the blue function. That gives us the length of this distance between the two. So just like in the previous presentation, when we do f of x minus g of x, we get negative 5x squared plus 40x minus 75. So this is going to be our side length. So then to find the area of each cross section, we're going to take that side length, x squared plus 40x minus 75, and square it. The area of a square is just the side length squared. So this is our integral. So go ahead and punch it in your calculator and see what you get for the volume of this solid. Alright, so when you punch it in the calculator, you get that the volume is 26.6 repeating cubic units. And on the last slide, we just have some practice problems from the book. There's only 2 of them. So I will see you all soon in class, and we'll talk more about this. Thanks.